Ladies and gentlemen, it is question and answer day for chapters 4, sections 3, 4, and 5. What questions do you have for me?
Number 26. When you calls for the critical values that it's zero real numbers and students on five. This is natural law.
Right.
So it's not in an interval and the mean that only have just about sense.
I'll still have an interval with an increase and a decrease, right? It'll just be open on the end where 0 is. Because the domain of that function doesn't include 0, right? So when I look at the domain of the function, I'm only allowed to look at numbers that are bigger than 0, right? So anytime I look at an interval of increase, an interval of decrease, look for a max, look for min, look for whatever I've got, it's got to be within that interval. And if there's only one critical number, that's all that's going on. It could be a flat spot. It might not be a max, it might not be a min.
Like a maximum value, but the value is zero,
Those are x values. If I want a min or a max value, I want the y value that goes with that point. 0 is not part of my domain. It can't be a critical number. Or nothing. Like a flat spot, right? If there's only one critical number, there's only one option to do stuff. That's why I'm forcibly restricted to looking at numbers within the domain of the function in my definition of a critical number. More questions? Yes, ma'am. Like number 60. Okay. 60 is a rational function. Do you want to look at 59 or 62? Which would you rather? Okay. 59, we are looking at the function 1 plus 1 over x minus 1 over x squared. Let's start with asymptotic behavior. Because that's what it says, right? Start with vertical and horizontal asymptotes. So, where is this function undefined? What's going to cause that to go? Okay. So I would expect a vertical asymptote at x equals 0. And that's the only number, as far as I can tell, where that's going to occur. How do I get horizontal asymptotes? I'm looking at it that way, right? So let's take the limit as we go to infinity and minus infinity. This is a rational function. It's just been broken apart, right? So there can be at most 1. What happens as we go to infinity should be the same thing as what happens as we go to minus infinity. I'll check them both anyway. What happens to these fractions as x gets inordinately huge, whether that's positive or negative? They get to be itty bitty teeny weeny, effectively going to 0. So this limit is 1 in both directions. And that means that the line y equals 1 is a horizontal asymptote. Automatically, I know some interesting things about my picture. As I extend the graph, it's going to close in on 1. I don't know whether it's going to be doing it from above, below, wiggling back and forth across it, but it's going to narrow in towards 1, both to the left and to the right. And there'll be this big undefined asymptote in the middle. Part B, intervals of increase and decrease require me to have what? Say again? Shalanta, what was that? Oh, I'm sorry, I'm hallucinating. What do I need to find intervals of increase and decrease? I need critical numbers. Critical numbers come from my derivative. The derivative of this function is if it helps, rewrite the original function. The original function is 1 plus x to the minus 1 minus x to the minus 2. Then I can do my derivatives with the power rule, which makes it faster. What's the derivative of 1? Derivative of x to the minus 1 is minus 1 x to the minus 2 minus becomes plus 2x to the minus 3. Here's another case where I say I'm going to do something with my derivative. If I'm going to do something with my derivative, I should simplify it, which means in this case, I'm going to go back to the quotient version. And then I'm going to find a common denominator, which in this case will be x to the third. And combine them. So I have two different kinds of critical numbers. Places where this function is equal to 0, places where this function is undefined, provided they are in the domain. But we've already excluded 1 point from our domain. And that happens to be the only place this derivative is undefined, where the bottom is 0. So I'm not going to count that anyway. But now I need to look at the top. Where's top 0? So now I need to make a sign chart. And that sign chart is going to contain the critical number and the place in our domain where we're undefined. I've used a dotted line to remind myself that's where the asymptote is, so I don't have to plug that number in. And now I put the top factor up here, the bottom factor over here. I pick a number in each section, and I plug it in and go to town. What do we get for signs in each of these 6 boxes? Then I multiply downward to tell me what the overall sign of f prime is.
Why did you so close?
Because there's still the asymptote in the middle, right? And behaviors can change there because I have to jump over it. I could go from increasing to decreasing. I could not, but I don't know. And since there's that big hole in the middle of my graph, I need to know what's going on each side of it. So where am I decreasing? Those are points. I want an interval. So I think of, I'm decreasing wherever this is minus, right? So let's look at the section of the x-axis that I've got here. This section is everything less than 0. It doesn't include 0, but it goes all the way up to 0. And this section is everything above 2. That's where the fence is. So I'm decreasing on the interval from minus infinity to 0, or from 2 to infinity. And the plus is an increasing, so I can write down the other interval that's left behind. And I'm increasing on 0 to 2. Emily, again, notice I'm using open intervals. So I'm not including 0. I'm not including 2 because technically I'm not increasing at that point. I'm not decreasing at that point. I'm looking at the sections between the vertical bars on my graph, my chart. Hey, part C, maximum and minimum values. Do I have a maximum or a minimum or both? I've got a maximum because the point 2 is an available point for me to plug in. I'm going up and coming down. That means I must be at the top somewhere. I don't have a minimum. I'm going down and I'm coming up, but there's a hole or a jump or an asymptote in the graph there. There is no point for me to use. That's why that dotted line is there. But it doesn't just ask me where the maximum occurs. It asks me for the maximum value. How do I find that? Plug it in. Take 2, plug it into the original equation. One plus 1 over x minus 1 over x squared is 1 plus a half minus a quarter, which is 1 1/4. So far, so good? Not short. Part D, concavity and inflection points, right? To do concavity, what do I need? Second derivative. Which means I need my second derivative. I go back up to my first derivative in the power rule form because it's easier to take the derivative there. And I go, okay, the derivative of minus 1 x to the minus 2 becomes 2x to the minus 3. The derivative of 2x to the minus 3 becomes minus 6x to the minus 4. That's disgusting. Let's play the same trick. I need to set this equal to 0. I need to know where it's undefined. It's better as a fraction than it is like this. Flip these under. Give me a common denominator. And I find myself in a wonderful position. I have two possible values where this is undefined or equal to 0. But one of them isn't in the domain again. I can ignore that one. It's going to have to be part of my chart, but it's not technically a point of inflection. Where's the top equal to 0? So that's my other possible point of inflection. And again, I'm going to pick a value on each side of each of those lines and plug it into the second derivative. Because my second derivative is written like this, I'm going to do the same thing I did in the first derivative. I'm going to write each piece on a separate line, and I'm going to multiply down once I come up with all of the pluses and minuses in that box. Again, pick numbers on any side, and plug and chug. I am taking these and raising them to the fourth power. That's an even power. Anything raised to an even power is automatically positive. That was easy. So it's really just the top one. -2 minus 6 is -8. 2 minus 6 is -4. 8 minus 6 is +2. I have a negative second derivative, I'm concave down. I have a negative second derivative, I'm concave down. A positive second derivative, I'm concave up. I changed concavity at a point. That's my point of inflection. If it's point, I need a y value. How do I get the y value? Go back and plug into the original equation. F of 3 is 1 plus 1/3 minus 1/3 squared. That's a ninth. A common denominator there is 9, 12. So it's 1 2/9, which gives me 11/9. 1.22222, infinite repeating decimal. I've now done all the work. I should draw a picture. How many points do I actually know the value of on this graph at this point in time? That's it. I know the local maximum, and I know my inflection point. The only things I know are where the asymptotes are. So really, all I have for a picture at the moment is very limited information. I know there's a vertical asymptote at 0. I know the maximum is a value of 1.25 at 2. I know the inflection point is just barely lower than that. 1.2222, oh boy. I also know as I keep going out in this direction, there's a horizontal asymptote there. There's also a horizontal asymptote on this side in this direction. at a height of 1. Oh, joy. So let me see if I can try and make a really crappy sketch in my head before I put anything to paper. I'm supposed to be sign chart. Decreasing, increasing, decreasing. I'm supposed to be concave down, concave down, concave up. My first reaction is, if I'm going to be coming up here, and I should be concave down and increasing, I should be curving upward. Yes? As I go up, I should have this sort of curve here. I should then still have that same curve until I get to there. Then I should kind of flex, right? Inflection. I should stress the curve at that point and start to bend the other way. What should be happening on the other side? You should be going down the whole time, and I should be approaching this line as I go that way. If I'm always going down, can I ever come above that line? As I go to the left, could I ever clear this line? If I did, I'd have to come back down, wouldn't I? And that means going to the right, I'd be going up. I'm going down on this whole side. I have to stay below this line the whole time. So I think of what's going on over here, kind of looking like that. I have absolutely no idea what those x-intercepts are. I could probably figure them out. But let's see if I'm even remotely close to right. One minus 1 over x plus 1 over x. I've forgotten already. Plus 1 over x. Minus 1 over x squared. This is what I think the picture should look like. Before I hit graph, what window should I look at to see all this important stuff? I really don't need a big Y window, do I? I don't need to go much above 1. So let's only go up to, say, 2. I don't really need to keep going down forever. I probably don't need to go much below, say, -4 or so, just to make sure I'm going down in the middle there. Out to the side, well, all the interesting stuff is happening between like nothing bigger than 3 or 4. Let's go out to 5 in each direction, just so we can put the neat stuff in one spot. I do see the bend. I do see this side coming down. As a matter of fact, if I keep going out a little further, I can see the change in the concavity. Oh, it's really hard to see, isn't it? We're concave down here, but we sort of flex and come back up. That's not a big gap between the peak here at 2, 1.25, versus at 3. If I zoom in the Y a little, I really can't see much about what's going on there in that curvature. It's really very slight. Not bad for a half-assed sketch. Do I want a perfect sketch? No, I want you to tell me where everything interesting is. When it says draw the picture, do it here. Better? Absolutely. 46 in 4.4. How about 47? Limit as x goes to minus infinity, x cubed e to the minus x squared. So we're in our L'Hopital's rule section. Let's think of each piece of this separately. Limit as x goes to negative infinity of x cubed. What's that going to give me? But it's negative and it's raised to an odd power, so it should stay negative. And if I think of the graph of x cubed, as I go off to the left, that keeps going down. So this is going to be a minus infinity. Limit as x goes to negative infinity, e to the minus x squared. Okay, wait a minute. That's e to a negative something. E to the negative. There's my graph of e. What happens as e goes to the negative side? So this is really 0 times negative infinity, and that sucks. That's the indeterminate form. And when I see an indeterminate product, my brain says I want to convert products to quotients because L'Hopital's rule only works for quotients. So I either need to rig this to become division that looks like 0 over 0, or rig this to become division that looks like infinity over infinity. But I have e to a negative power. What happens with negative powers? They go into the bottom, which means I could rewrite this as division fairly directly. Now, we know that the top of this is going to minus infinity. As x gets larger and larger and larger, what is happening to the denominator? E to the x squared. X squared is now positive. So I think of e to the x squared, that's going this way on the graph of e to the x. That's going to infinity. Yay! Out comes my buddy L'Hopital's rule. What is the derivative of x cubed? Yay! What is the derivative of e to the x squared?
Yes. 2x and x squared.
Chain rule. E to the stuff, derivative of the stuff. Simplify what you can. What can be simplified here? I can cancel an x. So now we try and evaluate this limit. As x goes to minus infinity, what happens to 3x? It's blowing up being negative. This, on the other hand, is e to the positive thing, because it's still x squared. That's multiplied by 2. That's still positive. It's going to infinity. This is still infinity over infinity. So what do I do? I'm sorry, what? Take the next derivative. L'Hopital's rule again. Fortunately for me, this is where it ends. Because the derivative of 3x is 3. That's not infinity. That's not minus infinity. That's not zero. I'm pretty sure I'm not going to get an indeterminate form again. What do I get on the bottom? Oh, I do the derivative of e to the x squared, which is what we did right here, isn't it? Now, the top is a number, 3. What happens to the bottom as x gets bigger and bigger and bigger and bigger? Murmur, murmur, murmur. Somebody speak up. It goes to infinity. So if I have something that is finite divided by something that is getting bigger and bigger and bigger and bigger, what is the overall result? I don't know what you mean by can't use. Can't use the negative fraction. Well, then I have to do some algebra to rewrite it. Like in the problem you were asking me about, there's an x, right? That's going to 0. If I move it to the bottom, negative powers get moved to the bottom and become positive. Positive powers, when moved to the bottom, become negative. So I can move something from the top to the bottom as long as I change the sign of the power. So I take that x that's on top, put it on the bottom, make it an x to the -1. Which absolutely does change the way it behaves. Better? Wonderful. More questions? Yes, Andrew. Oh, yes. Now, this is where I said we were going to have to review dividing. So, do you want to do 67 or 65? 67 says, two x cubed minus 5x squared plus 3x over x squared minus x minus 2. And I'm looking for a slant asymptote. Because the power on top is exactly 1 bigger than the power on the bottom, I want to fix this fraction. This is an improper fraction, 5/3, 17 over 10. I should be able to write it as a mixed number. If I had the fraction 5/3, that's 1 plus 2/3. How did I get from 5/3 to 1 plus 2/3? I promise this is not as stupid as it sounds. I didn't multiply by 3. I actually took the 3 and divided it into the 5. How many times does 3 go into 5? It goes 1. So you multiply the 1 and the 3, you subtract, you get a remainder. And that's the 2/3, isn't it? I'm going to divide the bottom into the top. It's the same damn procedure as this. Only I start with just the first terms. How many times does x squared go into 2x cubed? Well, if I cancel the x squared with the 2x cubed, what's left? Now multiply everything through. 2x cubed, 2x times minus x is minus 2x squared, minus 4x, and now you subtract just like we subtracted here. The 2x cubes cancel. 5x squared plus, okay, that's going to be negative 3x squared. These powers are still the same. I can divide again. So what I end up with is a quotient and a remainder. Right? Now, why do I think of this as an asymptote? What happens as x goes off to infinity to this piece? Which means as x gets bigger and bigger and bigger and bigger, this function gets closer and closer to looking like that, doesn't it? So the line that is left is my slant asymptote. Yes, ma'am. Well, as x gets bigger and bigger and bigger, this is going to be x over x squared, right? So which power wins out? Which means the bottom is bigger than top, which means we're going to go to 0. So as x gets bigger and bigger and bigger, this piece becomes useless. As a matter of fact, if we were to then graph the equation we started with, which was 2x to the third minus 5x squared plus 3x, all divided by x squared minus x minus 2. I'm going to graph this. I'm going to graph this on a fairly big window. We'll start with the standard window, and then we'll make it bigger. I don't see very much here, right? There are asymptotes in the middle of this thing because there are places where the denominator is 0. But now I'm going to graph that line. As we go further and further out, we're getting closer and closer to that line, aren't we? Son of a... That's what an asymptote does. It gives me our tendency as we go off to infinity and to minus infinity. Now, in this case, I can go out a lot further. And I can see we get really, really close the further we go out, don't we? If there are gaps between items here, under the radical, and outside the radical, if there are gaps here, I'm going to have gaps in this piece, aren't I? My goal is to always line up the powers. If it isn't getting closer to 0, I haven't finished my division. I don't stop here until this power is smaller than this one. And that guarantees me that the power on top will be smaller than the power on the bottom. Yay! That's how I know it's going to go to 0. Just like up here, I knew I could stop my dividing because 2 is smaller than 3. I can stop my dividing because my power in my remainder is smaller than the power in my divisor. Polynomial long division was an Algebra 2 topic, so it's been at least a year, maybe 2, maybe 3 since you've seen this. If not, I don't remember doing this at all. Whole different ballgame. This division idea even works if the power is higher. The difference between powers is bigger than 1, but then my asymptote isn't a straight line anymore. And that's a weirder idea. We'll talk about that method of approximating other functions in discrete math next semester if you're taking that. But there's a whole idea about asymptotic behavior and its utility in long-term behavior of functions, things like growth functions. We talked about our exponential growth function. There's a whole other set of growth functions, harvesting functions, culling, seeding functions that are all related to this idea. and their long-term behavior is a trig function. What's happening with the sunshine out there right now? For the past several weeks, it's been happening with the sunrise. Been getting later and later and later, right? So the number of hours of daylight has been getting smaller. And then later in the year, it's going to get bigger again, right? So the number of hours of daylight is a trig function. That's a steady state long-term behavior. That's an asymptotic relationship to the actual numbers of hours because it isn't a perfect sine curve. Anyhow, lots more interesting stuff can be done with this division idea. Better? Whoever asked this one. Parsa, you had a question as well. 34. I may not be able to do 34, but I can do 33 or 35. Let's take a look. 34 itself. Well, let's look at 35. It's a very similar idea. The whole goal is the repeating of L'Hopital's rule. I may have to do it 3, 4, I don't know how many times. As long as I still have an indeterminate form, I keep going. So 35, ln of 1 plus x over cosine x plus e to the x minus 1. And we're taking the limit as we go to 0. I think I got robbed. Really? Do I have a sign error here? What's ln of 1? What's cosine of 0? What's e to the 0? This problem didn't need L'Hopital's rule at all. I'm done. I got robbed. It's just 0. It's not an indeterminate form. Damn it. But 34 is an indeterminate form. And we end up doing L'Hopital's rule lots more than once because the product rule on the bottom. Zero, 1. 36 probably works the same way. Do you want to try that one? Wait a second. No, 34 is not an assigned problem. I can do 34. Let's just do 34. It's not an assigned problem. Here I was thinking it was an assigned problem. E to the x plus e to the minus x minus 2 cosine x over x sine x. When I put in 0, I get 1 plus 1 minus 2 over 0 times 0. Well, that's definitely 0 over 0. So by L'Hopital's rule, what's derivative of e to the x? Yay. What's derivative of e to the minus x? Derivative of cosine? Product rule on the bottom. Okay, e to the 0 is 1. Minus e to the 0 is 1. plus 2 times 0 over 0 plus 0 times 1. It's still 0 over 0. Do it again. There's a minus here. When I do the chain rule, I'm going to get another minus, so I'm back to plus. The derivative sign. Derivative sign is cosine. The derivative of x is 1. Derivative of cosine is minus sine. What happens when I plug in 0 this time? That's a number. I'm done. Best part about L'Hopital's rule, as long as it's indeterminate, do it again, do it again, do it again. And it certainly makes me practice all my derivative rules. Completely understandable. This is what is going to trip us up a lot. A sign error can take a page to find. You get a result, you're like, that doesn't make a damn bit of sense. What the hell did I do wrong? And you go back, it's on line 3 or something. I will speak from personal experience. For my PhD thesis, I got all the way to actually defending, which is where you go up in front of the group of other PhDs and tell them what you did and why it's new and interesting. And they found a mistake on page 6, 95. The problem was my advisor had chapter 1, which went through page 15, for about 7 or 8 months at that point and had missed it himself. So they had a lovely discussion with me about why this was broken and if I could just fix this one little piece. 6 months later, I'd rewritten my entire thesis. It took me 6 months to fix it. It wasn't fixed. I turned the entire thing on and said, not only is this broken, it's completely, then here's why. So the entire idea had to be thrown out. Trust me, find the little mistakes. I was very happy Frank found it, but couldn't you give it to me more than the morning of? Okay, this is due tomorrow. And tomorrow we start another application that's going to take a while and is going to require you to bring in outside knowledge. Just like our related rates problems, optimization problems are things we need to know about the real world. See you all tomorrow.